Co-17C. Today is October 5th. All right. So let's say we have a function that looks like this. I'm going to just make something up. Let's say it's, I don't know, 2x plus y over, let's say x minus 7y. And the first thing I'll say about functions like this is, with rare exception, your range is almost always everything. Well, let's talk about the domain first. So the domain here, there's no roots, there's no logarithms. The only thing we have to worry about is the potential division by 0. So our domain, we need to exclude where the denominator is equal to 0. And being a person like many of you who has grown up writing y as a function of x, because that's how we usually write things, I would solve this for y. So I would write it as negative 7y equal to negative 7y equal to negative x, y equal to 1/7 x, or x divided by 7. So that's not in the domain. So here's what my domain looks like. It's literally everything except for this line. I'm going to try and draw it the best I can. I'm going to draw it dashed because I'm excluding it. So here's my line. Y equals 1/7 x. And here's my domain. Everything else. And if I was using words to describe my domain, I would describe it as the entire xy plane minus a line, or except a line, or right, however you want, whatever words you want to use. And again, just because I can't not write this, if you were writing the domain, you would write it as the set containing all points x comma y, such that y does not equal 1/7 x. Every other point is a-okay, but we can't have 7,1 or 14,2 or 0,0 or any y comma 7 times that for x. Yes. No. So here's the thing. For domain, for functions of more than one variable, we cannot write the domain as an interval. It's not an interval. It's a region in the xy plane. And so the only way to describe I will say the most concise way of describing it is exactly what I've written here. This is the best way to write the domain if you're trying to actually write it as something. But it's a set of coordinates, right? It's not just an x value. Like you might say, well, James, can x equal 28? I'd be like, well, yes, as long as y isn't 4. It's totally fine for x to be 28 most of the time, except for one particular point on that line, x equals 28. So that's why we have to write it like this. Let's talk about the range, because the range is certainly what's more challenging here. Oh, that's interesting. Oh, interesting. Cool. So now for the range of f of xy equal to 2x plus y over x minus 7y. So here's what I would say about the range. There's a number of ways to approach this, but I think the way we did it first last time was actually the best, with the perspective that if you're going to have to find the level curves as well, you might as well set this thing equal to c and then try and do the solving like we did last time. So we're going to set our function equal to c. And then you're going to do one of two things, in my opinion. The first thing you're going to do is you're going to look to see, do I have x squared plus y squared, or negative x squared minus y squared showing up? If you have either of those two things, your job is to solve the equation so that you isolate x squared plus y squared on its own. Because then you're going to get x squared plus y squared equal to some stuff, which is the equation of a circle, whose center is the origin, whose radius is the square root of whatever. But here, we don't have that. There's no x squared plus y squared. I will just say, in contrast, if you look at something like, sorry, let me grab, just so like, for example, question 5 from the homework here, where you have e, oh, by the way, in case you didn't know, exp means e to the power of negative 2x squared plus y squared. When you're finding the level curves there, you should set that equal to c, and then try to isolate the x squared plus y squared. So you get x squared plus y squared equal to, I don't know, like the natural log of c divided by -2. That's a circle, center of the origin, radius of the square root of the natural log of c over -2. Similarly, I think there was another one here as well. Maybe not. I could be mistaken. But that's the idea. If you see an x squared plus y squared, you should be thinking, oh, my level curves are probably looking like circles. I need to isolate x squared plus y squared so I can figure that out. But we don't have an x squared plus y squared here. So if you don't have an x squared plus y squared, the next best thing to try and do is to try just to solve for y. So I'm going to isolate y. Now, well, yeah, we'll do that first and I'll talk something else as well. So let's see. So if I'm going to solve for y, I'm going to multiply both sides by the denominator. So I'm going to get 2x plus y equal to c times x minus 7y. I'm going to distribute the c. So I'm going to get c times x minus 7cy. I'm going to bring all the y's to the same side. So I'm going to have a 7cy plus y equal to a c times x minus 2x. Factor out a y. And you might as well factor out an x over here as well. To get y times 7c plus 1 equal to c minus 2. And finally, y equal to, I like to write it like this. I like to write the c minus 2 divided by 7c plus 1 on its own times x. So here's the point. The point of this is that what we're saying here is I can set this function equal to a value of c, and for any value of c, except for maybe 1, I can certainly find a y and an x value that gets me that value. So for example, someone throw out a random c number that isn't -1/7. Anybody? 2, sure. So I set c equal to 2. I can go 2, okay, fine. They'll still work. I can go ahead and set y and x equal to numbers that'll work. So I'm going to get y equal to 0 times x. Because 2 minus 2 is 0. I'm going to ask for another number here. But so basically, x could have been 5 and y could be 0. And those values will get me a c value of 2. Meaning that value of 2 is in the range. I found x and y coordinates that got me the output I decided I wanted. If I pick something else, like, I don't know, c equal to 17, the same story. I'm just going to throw my 17 in for c there and say that y is equal to 17 minus 2 over 7 times 17 is 119 plus 1 is 120. And that actually reduces to 1/8, I think. Yeah. Not that you need to do that. But then you can pick any x and y value that you like that satisfy that equation. So for example, I could pick x equal to 8 and y equal to 1. And if you throw those back into the original function, let's see. 2 times 8 plus 1 over 8 minus 7 times 1. Oops. No, that's right. I happened to pick a nice number. I lucked out. Is 17 over 1. So the point of doing this is so that we get to see that as long as I can pick a c value that doesn't screw this part up over here, I can always get that c value picking some x and y that work. And I didn't have to pick 8 and 1 here. I could have picked 16 and 2 or 24 and 3 or anything where x is 8 times y. However, there is one value of c, at least according to the work I've done so far, that might not be in the range. I don't know about c equal to -1/7. Because if you plug c equal to -1/7 in there, you get division by 0, which is a problem. There's a couple ways to go about doing this. And the easiest way is to look at your original function, and usually it's setting x equal to 0 if you solve for y, and decide which of those two things you need to set equal to 0 to make the function equal to -1/7. Oh, look, if we set x equal to 0, your f of 0 comma y is going to be y over -7y. And as long as y isn't also 0, which it doesn't have to be, you can pick any value for y you want. That's going to equal -1/7, as long as y doesn't equal 0. And what that shows us is that we do get every possible value in the range. So our range here is everything. And again, I will remind you all that when you're looking at questions like this and they ask you what's the range, and then later on they ask you what are the possible values of the c in your level curves, these answers are the same. Right? To be a possible c level curve value, has to be a value that was in the range so that you can set the function equal to it and actually get a solution. Not the last thing I'll say. The other thing I'll say here is if you really, really wanted to, you could have gone back. It's more work, but we could have gone back and actually solved this for X instead of solving for Y. So we got time. I mean, it's always easy to say at the beginning of class. Let me just show you what that looks like so you can see what I mean. So at this point here, if instead I decided to solve for X, I would have, let's still bring the X's to the right. In fact, let's go down one more. Yeah, let's go down to there. Now, if I solve for X, you get Y times 7C plus 1 equal to X times C minus 2. And I'm going to divide by C minus 2. So X is equal to 7C plus 1 divided by C minus 2 times Y. And now we can see that, oh yeah, C being negative 1/7 is totally fine. C equal to 2 looks like it could be problematic there. We know it's not, but it could have been. So here, C equals negative 1/7 is A-OK. And I will point out, C equals negative 1/7 corresponds to the level curve. Well, what do I get if I plug in negative 1/7 for C? Over here, what's this part going to be equal to if C is negative 1/7? Right. So you get the level curve X equal to 0, which is a straight line that's vertical and doesn't correspond to having a defined slope. So that's why over here, C equal to negative 1/7 was problematic, because you're getting still a level curve that's a straight line, but it's a straight line with an undefined slope. So that's why it's an issue that we have to kind of look at. I don't know exactly how your instructor wants you to go about doing this, but in my opinion, this is the way I would do it. And the reason I would do it this way is because then when you're asked to find the level curves, we've already got the work done. Our level curves, well, if we look back over here, we've got Y equal to C minus 2 over 7C plus 1 times X. Or in other words, Y equal to some M times X, where M is that right there. And we know that Y equal to M times X is a bunch of straight lines through the origin. I don't really think I should say straight lines. A line, when you say line, we know we mean something straight, but I said straight line, so oh well. You don't need to clarify that a line is a straight thing. It is already straight. A bunch of straight lines that all cross the origin. So that's the reason why I recommend finding the range this way, because it also then kind of gives you, hopefully, what the level curves are going to look like. Yeah, it's a good problem. Let's kind of keep things in order here, James. Questions about any of that before we start talking more about limits? Yeah. Yes. Right. Not really. I would say, unfortunately, there's no like one thing that works to find the range. It's always kind of like, I'm going to try this time. I'm going to try this time. Like you kind of are just, for me, the thing I do first for the range is I kind of look at things like, is this something where I can just make like the output as small as possible by picking a convenient value of X and Y, and the output as large as possible by picking a convenient value of X and Y. For example, if you have a function like f of xy equal to the square root of 64 minus x squared minus y squared, I can find the range really easily by saying, okay, well, I can make this as small as possible by choosing x and y to be not 0 and 0, 0 and 8. And you get the square, and you could pick 0 and -8, or 8 and -0, 8 and 0, 8 and 0, or -8 and 0, or some other numbers that when you square them and add them together, you get 64. But here I'm getting 64 minus 0 minus 8 squared, which is the square root of 0, which is 0. And we also know that for square roots, the lowest possible value you're ever going to get is 0. You might not get that low, but certainly you can't go any lower. And then to make it big, I would let x and y be as small as possible, so I'm not subtracting off anything. I mean, 64, square root of 64 minus 0, which is 8. So here my range is relatively easy to find. It's everything from 0 to 8. Some functions are quote unquote easy like that, where you can be like, oh yeah, I know what makes this small, I know what makes this big. Jocelyn. What I think I was referring to was the fact that just to see that the negative one set, like, so there, I was referring to the fact that there's a couple different ways you can see that negative 1/7 in this particular example is okay. The easier way is just to be, is usually when you've got something specifically like this, once you solve this for y and seen what the problem is, it's almost always just looking at this and setting x equal to 0. Because if x is 0 and y is a 1, for example, the function value is negative 1/7. Yeah. If you want to show something's in the range, one way of doing it is picking an x and a y that when you plug it in, just spit out that value. And that is a valid way of showing that negative 1/7 is in the range. So for example, here, I could say f of 0, 2 is 0 plus 2 over 0 minus 14, which is negative 1/7. And that shows that negative 1/7 has to be in the range because I found values of x and y in the domain that give me that value. Well, so here's the thing. Normally, I don't want to do this, right? Because how many values are actually in the range? An infinite number. Almost always. There's almost never a time where the range is like finite. Kind of, yeah. But here's what I'm pointing out. The work we did here showed us, remember, C is the range values. So the work we did here showed us that we could get any C we wanted, except for maybe what? Negative 1/7. It was the only problem here. Any other value of C, we are confident that we can find an x and a y value that will give us that. Because you can pick any value of C you want. Somebody picked 2. I picked 17, but you can pick anything. You can pick 1,000,000,005, plug it in for C here, and find and set x equal to 1, and then find the corresponding y value. And that x and y value will give you that C output. But looking at this, there is one potential issue, and that is the C value of negative 1/7. Right? Looking at this, I can't plug in C equal to negative 1/7 because I get y equal to something divided by 0 times x. So I can't just find an x and a y that make that work. So what I do, and this is pretty typical, is I look back at my original function because I'm lazy, and I just say, oh, look, I see that the y's, if I just look at the y terms and ignore the x term, if I divide those by each other, I get negative 1/7. That's what I'm going to do. And this usually works for this. It's not 100% always going to work, but most of the time for this kind of thing where you have something times x plus something times y over something times x plus something times y, just eliminating the x's is going to work. So I'm going to let x equal 0 and then y be anything except for 0 because you can't make them both 0 or you'll have division by 0. And then you're going to get that missing range value. So that's kind of the fastest way of doing a problem like this to show that everything. It takes a little practice. So I would encourage you to write yourself up another problem like this. Like give yourself something like, I don't know, g of xy equal to x plus 4y over 13x minus y. And try that out. And you'll probably be missing 13 from your range. And then you'll have to show that 13 is actually in your range. You'll probably be missing -4 from your range. Sorry. Probably missing -4 from your range, and you'll have to show that -4 is in the range. I would encourage you all on your own to do that. It's worthwhile. Other observations. Yeah. So what I'm saying here is -4. So if you did the same sort of work here, I'm pretty sure you would see that -4, you get something like this, except you have like C plus 4 in the bottom. The -4 in the sheet. But then you can look back in here and say, okay, well, what value of x and y can I pick that will easily make this function equal to -4? What should I pick for x? 0. And then if x is 0, I can pick like 1 for y. And if x is 0 and y is 1, I get 0 plus 4 over 0 minus 1, which is 4 over -1, which is -4. So what I'm saying is that C value that's not always obvious is usually easy to find by plugging in 0 for X and whatever for Y.
And the reason we also recommend this is because when we get it into that form, basically the one equals MX form, we can just calculate all the values.
That's showing you the level curves as well. Yeah, exactly. So it's twofold. Let's see what's happening in the chat here. Sorry. Oh, and I'm sorry, my video. Sorry about that. Let me pin myself here. So the Y over -7. Oh, cool. You got it. Great. Sorry about that. There we go. Oops. There we go. Yeah. Yes. Yeah. Cool. Right on. Okay. Other questions about this one? Let's talk about some limits. And also we'll talk about continuity a little bit. Because they're very related to each other. Let's see, where am I? 1 second. Let me grab some stuff. We've got too many papers. Yeah, partial group. So let's look at some limits. Yay. I have to remember which ones we did last time. Oh, I know. Sorry. Let's put these. Cool. Yeah. So let's look at something like this. Here's a fun one. The limit as x, y approaches 2, 3 of 3x squared plus xy minus 2y squared over 3x minus 2y. And if you had to guess, what do you think is going to happen when I plug in 2 and 3 for x and y? Am I going to get a nice number? Probably not. I'm probably going to get 0 over 0. It's going to happen a lot. It's going to happen most of the time. So let's see. Let's just double check. If I plug in 2 for x and 3 for y, I get 3 times 4 plus 2 times 3 minus 2 times 9 over 3 times 2 minus 2 times 3, which that's 0 over 0. This one is not a good candidate for checking paths because we're not going through the origin. That doesn't mean you couldn't, right? There's a number of paths that go through this. Here are some paths that we could check if we wanted to, but we're not going to. You could pick the path x equal to 2. You could pick the path y equal to 3. You could pick the path, I don't know, 2, 3. You could pick the path y equal to 3/2 x. Sure. Those are all valid paths that you could try. I'm going to tell you right now, they're not going to yield anything different. Every one of these paths is going to give us the same limit because this limit actually exists. So when you have something like this, it looks like it might factor. So here's the thing. I recognize that 3x minus 2y gives me a 0 when I plug in 2 for x and 3 for y. So I would really, really, really like for that same factor to show up in the numerator. So I'm just going to guess that it does. And then I'm going to figure out what the other piece needs to be and check that it actually works. So if I need a 3x squared here and I have a 3x here, what do I need there? What do I need to multiply by 3x to give me 3x squared? Yep. And then I'm ignoring the middle term. If I have a negative 2y here and I need a negative 2y squared, what do I need over here? Plus y. And I'm going to check to see if the middle term works out. So my middle term would be 3xy minus 2xy, which is equal to 1xy, which is exactly what I have right there. So I'm good to go. That's really a nice way of trying to factor something, because here's the thing. If you know that plugging in a certain value for x and y gives you 0, it means the thing that it made 0 is kind of the factor. So I know that when I plug in 2 for x and 3 for y, I'm getting 0. That means that 3x minus 2y is probably going to have to be a factor. Yeah. Right. So here's the thing. When your coordinate isn't 0, 0, usually choosing paths is not going to be the right method because it's not easy to find the paths. And usually the questions are asking away where these limits actually exist. So I could have done the work, I could have done more work and be like, let's try the path x equals 2, let's try the path y equals 3, let's try, but I would have gotten the same value every time. And that's not enough to show the limit actually exists. Show the limit exists, I have to do something else, like factoring and canceling. So here, these divide to 1, and I'm left with the limit as x comma y approaches 2 comma 3 of x plus y, which is just 5. So this limit is 5. And if you chose any of these paths, you would also get 5. It's kind of neat. Let's see here. Sure. Let's look at something like, so here's kind of a contrast to that. Let's look at the limit as x, y approaches 1, -1 of x plus y over x, y plus 1. Which again, not terribly surprisingly, is a 0 over 0 type of limit. You plug in 1 and -1 for x and y, you get 0 on top, you get 0 on the bottom. And here we are going to try some paths. So I'm going to go through the point 1, -1. I always think, especially if you're going through the point that's not on the origin, or not the origin, you should try the two constants. You should try the x equals 1 line and the y equals -1 line. Because it's always just an easy thing to do. It's kind of the easiest thing to do if you're trying different paths. So if we try x equal to 1, we're going to get the limit as y approaches -1 of 1 plus y over y plus 1. But what's 1 plus y divided by y plus 1? Right. If you have something divided by the same, I know it's written differently, but 1 plus y and y plus 1 are the same. And when you divide something by its same self, as long as it's not 0, its division is going to be 1. This is the limit as y approaches -1 of 1, and the limit of a constant is the constant. Let's do the same thing, except now we're going to pick the path y equal to -1. So if I do that, I'm going to have the limit as x approaches 1 of x minus 1 over x times -1, which is -x plus 1. And to be a little bit more expository, if I factor out a -1 from the top, sorry, from the bottom, either way, really, but I would actually pick the bottom, x minus 1. If you factor out a -1, you've got x minus 1. X minus 1 divided by x minus 1 is 1. So this is the limit as x approaches 1 of 1 over -1. And the limit of a constant is just the constant. And 1 divided by -1 is -1. So we can see that these different paths give us different values, which means the limit doesn't get to exist. I would say you are, of course, always welcome to take pictures. I also do post the class notes on Google Drive, so you're certainly welcome to take pictures, really. But like, just so you know, you don't have to if you don't want to, because they will be posted and easily accessible. So, but again, you're welcome to if you want to. Cool. So let's look at some examples that are more in line with what we're usually doing. Something like, yeah, let's do this. So let's say we have this function, f of xy equal to x cubed y over x to the 6th plus y squared, as long as x, y is not 0, 0. And then this is equal to 4. Sure, 4, why not? When x, y is equal to 0, 0. So I just want to point out that this function is defined at 0, 0. Because we defined it. F of 0, 0 is 4. So now let's look at the limit. So does the limit as x, y approaches 0, 0 of f of x, y exist? Probably not. Usually, if you had like just in general, if you had to bet on whether or not one of these limits would exist, I would always bet no. That would be my default position. Bet no, the limit doesn't exist. More times than not, you'll probably be right. So I don't think it exists. So I'm going to start trying different paths. And I'm definitely always going to try at least one of the paths that goes through either x equals 0 or y equals 0. I personally like y equals 0. So I'm going to use the path that goes through the x-axis, which is the line y equals 0. Excuse me. So we're going to take the limit as x approaches 0 of x cubed times 0 over x to the 6th plus 0. And as we've seen many a time, this ends up being 0, because 0 divided by something not 0 is 0, and the limit of a constant is the constant. And I think we can see that if we pick the other easy path, where x is equal to 0, we're going to get the same result. If x is 0, you're going to get 0 on top and 0 plus y squared on the bottom, which isn't going to change what the limit ends up equal. Which isn't helpful to us, right? Because if we think the limit doesn't exist, we need to pick a path that gives us a value that's not 0. So here's the intuition. You want to pick y equal to some power of x or x equal to some power of y, so that hopefully, and this doesn't always work, but it often works, people design these problems so it works, so that when you plug that in, you end up getting the same power of either x or y in the numerator, or I should say the same highest power of x or y in the numerator and the denominator. There is a nice choice I could make here. I could let, I have enough room? Yeah, I have enough room. I could let y equal x to what power? Yeah. So let me just point out, 2 is not going to work. If I let y equal x squared, I'm going to get x cubed times x squared, which is x to the 5th on top, and I'll get x to the 6th plus x to the 4th on the bottom. Not good. But if I let y equal x cubed, I'm in good shape, because then I'm going to get x cubed times x cubed, which is x to the 6th on top, and x to the 6th plus x to the 6th on the bottom. And I don't even need them to be the same on the bottom, as long as 6 is the highest power on the bottom. So that could have really been like a y there, and it still would have worked out just fine, I think. So if I do that, I'm going to get, excuse me, the limit as x goes to 0. Why am I not writing x, y goes to 0? 0. Well, let me show you what's happening here. If I'm substituting in x cubed for y, meaning x cubed times x cubed over x to the 6th plus x cubed squared. The reason I'm not writing x comma y goes to 0 comma 0 is because there aren't any y's in my limit anymore. So it doesn't make any sense to write that part. So once you replace something with either x's or a constant, you don't need to write the letter that's being replaced with something. And then we've got the limit as x approaches 0 of x to the 6th over, oops, that's an x to the 6th right there. Apologies. X to the 6th plus x to the 6th is 2x to the 6th, which is equal to 1/2. I skipped a step. I skipped a step. I didn't say that it was the limit of 1/2 equal to 1/2. I just said, I know that's going to be 1/2, and then the limit of 1/2 is 1/2. Yeah. I chose x cubed because of experience. Because I saw that when I plugged in x cubed, the power on top was going to be x to the highest power on top was x to the 6th, and the highest power on the bottom is also x to the 6th. That was the reason for my choice. Because when the degrees are the same, you end up getting this cancellation, you're just left with a constant after, which works out really nicely. Let me just actually that wouldn't work out there. And so I said something before that was actually not true. I really do need, if this part here, well, in fact, I'll show you what I mean in a second here, instead of trying to explain it with just words. So that means that the limit does not exist. Which also means the function isn't continuous at the origin. I'll also point out that f of xy is not continuous at the origin. Because just like in 17A, to be continuous at a point, the limit as x approaches that point has to equal the function value at that point. The same thing is true here. To be continuous, the limit as xy approaches 0, 0 of f of xy would need to equal f of 0, 0, and it doesn't. In fact, I'm going to state that a little bit more explicitly in just a second here. So what we're saying here is, yeah, we got room. So definition, f of xy is continuous at the point a comma b if the limit as xy approaches a comma b of f of xy is equal to f of a comma b. That's what it means to be continuous at a point. That the limit as you get closer and closer to that point is actually equal to the function value at that point. Let's see. Yeah, question.
Which additional element to have the one to use the line the essence x equals to 0.
So we could have, but it wouldn't have given us anything different. So if we had used that, in fact, let me just put it down here for a second. So for that previous problem, for f of xy equal to x cubed y over x to the 6 plus y squared, if I use the path that's the y-axis, I'm not saying it's wrong to use it, I'm just saying it's not helpful in this particular example. Because if we use the y-axis, we're going to get the, which is x equal to 0, we're going to get the limit as y approaches 0 of, let's see, I've got 0 cubed times y over 0 to the 6 plus y squared, which is the limit as y goes to 0 of 0 over y squared. 0 divided by y squared is 0, and the limit of 0 is 0. So the reason I didn't do it is because I knew that it was going to give me the same result as when I had used the x-axis. But since so here's the thing, I had kind of previous knowledge, right? I already knew from practice that this limit was going to not exist. So I didn't want to do more work than I needed to, because it's not helpful to know that the limit is 0 again, because I'm trying to show that there's a path where the limit is a different value. That doesn't mean it's not good to check, right? There are certainly times when the y equals 0 path and the x equals 0 path do produce different results. In fact, I think there's a couple homework problems that have that happen.
So if we narrow down the x equals to 0 and y equals to 0, the answer is all
the same.
So we can choose the
Right, you can use a different path.
so we choose to find the x equals highest power.
Or really, again, and again, it takes practice, but I'm looking to make a choice here so that I end up having the same highest power for the top and the bottom. Question? As long as it goes to the point. Yeah. So that's why the origin is so nice, because there are lots of easy paths. Y equals x squared, cubed, to the 4th, to the 5th, to the 6th, any power you want. Same deal, x equals y squared, cubed, to the 4th, to the 5th, any power you want. Or y equals 3x, or 4x, or 5x, or x equals 2y, or 3y, or 4y. Right? Lots and lots and lots. Or sine x, or the square root of x, although that's not really the choice. But let's see, and there's a chat here. Let's see what's in the chat. So the limit doesn't exist because, well, I would say it's not that it should equal 0, it's that we have different paths where one path that equals 0 and another path that equals 1/2. And since those paths are giving us different values, that's why the limit doesn't exist. But I wouldn't use the word should there, because it shouldn't be anything specifically unless it actually exists. What I would say, if I was really going to use the word should here, is the limit should have been 4 so that the function would have been continuous. That would have been ideal. Because usually we like continuity if we can help it. Let's look at some more examples here. What time is it? Okay. Let me throw maybe one more example your way, and then we will, yeah. Yeah, okay, let's look at this example. So here's, actually, let's look at that, sorry. Everything's everywhere, all of them. Let's go over here, yeah. Let me just grab this. All right, so there's a couple homework questions that I think are kind of neat, like something like this. You got f of x, y equal to, sure, let's say 4x squared, y squared over 2x cubed plus 7y to the sixth when x, y is not 0, 0. And then 0 when x, y is 0, 0. And the question is this function continuous at 0, 0? Interesting. That is interesting. So are we continuous at 0, 0? Well, certainly the function exists at 0, 0. We've defined it to be 0. So f of 0, 0 is equal to 0. The real question, the question that's really always the question in these kind of problems is, does the limit exist at the point you're talking about? And also, does it equal the value that we've defined the function to be equal to at that same point? So the question really is, does the limit as xy approaches 0, 0 of f of xy, does this equal 0? If the answer is yes, then the function is continuous. If the answer is no, then the function is discontinuous at that point. This function is continuous at most points, wherever it's defined. Real, like if you, like for example, this function is certainly continuous at 1, 2, because you could just say, well, the function value at 1, 2 is whatever you get when you plug in 1, 2, and the limit at 1, 2 is also the same number because you would just plug in 1, 2. All right. So I'm going to go with my usual assumption of thinking that the limit doesn't exist. I don't know if that's right, but it's the easiest place to start. So if the limit doesn't exist, I'm going to start looking at paths. So let's try the path y equal to 0. It's always a good path to try. So I'm going to do the limit as x approaches 0, 4 times x squared times 0 over 2 times x cubed plus 0. That's going to be the limit as x approaches 0 of just 0 over 2x cubed, which is 0, and the limit of 0 is 0. And now I'm not going to do x equals 0 because I can see that I'm going to get the same result. I can see that if I plug in x equal to 0, I'm going to get 0 on top and 7y to the 6 on the bottom, and the limit of that will also be 0, which doesn't help me show that the limit doesn't exist. I'm going to skip that. I don't know. I have a guess. Here's my guess. My guess for a path is x equal to y squared. Because if I do that, well, let's see what happens when I do that. So I'm gonna do the limit as I'm actually replacing the x. So here's what I would point out. I really don't want to use y equals square root of x, because that path only is on one side of the origin. It doesn't actually go through the origin. You're missing the other half of it. So it's better to always use the integer power as opposed to the rational power. I want y equals x squared, not x equals y to the 1/2. I don't want fractional powers. I want to do away with that and square both sides. So if I do this, I'm going to get the limit as y approaches 0. On top, I'm going to get 4 times y squared times y squared. On the bottom, I'm going to get 2 times y squared cubed plus 7y to the 6th. And I've lost a square up top here. I should have said 4 times y squared squared times y squared. And now look, I have made the rightest choice I could have made. Because if I do this, I get the limit as y goes to 0 of 4 times y to the 4th times y squared is y to the 6th. And on the bottom, y squared cubed is y to the 6th plus 7y to the 6th. So I have the limit as y goes to 0 of 4y to the 6th over 9y to the 6th, which is the limit as y goes to 0 of 4/9, which is just 4/9. Which means the limit does not exist. Yes. I know Mean Girls Day was like 2 days ago, but the limit does not exist. So, limit does not exist, which means the function cannot be continuous at that point. So f of xy is not continuous at 0, 0. The limit has to exist for the function to even have a chance of being continuous. I'm curious. I'm not that curious though. Yeah, I'm not that curious. Oh, let's see what's up. Let's see what's in the chat here. So it does not exist because there are 2 different values, right? So since the limit along this path ends up equaling 0, and the limit of the function along this path ends up equaling 4/9, and since those aren't the same, the limit doesn't exist. And it's almost always easier to show a limit doesn't exist than to show it does exist.
You just try again.
Yes. So that's the thing, is if you think the limit doesn't exist, you just have to keep trying paths until you get one where you get a different value. But if you do that enough times and you keep getting the same value over and over and over again, that's not great. That doesn't mean you can just say the limit is whatever number you keep getting. You cannot prove a limit is a number by exhaustion. You have to do some other work, like factoring and canceling, like in that previous example, or the squeeze theorem kind of thing we did last class, which I'm trying to look at the homework here to see if there's any examples where that really kind of happens. And I don't know if there are, which is kind of disappointing. Let me see one more thing here. Yeah, I don't know. That would always be my default assumption. At least I should back that up. Always when you're trying to find the limit, what should you do first? Yeah, plug in whatever the point is, right? Just like a socket, plug it in, right? Don't stick your fingers in the socket. Plug it in. If you get a real number, done. That's your limit. But if you get, in all likelihood, 0 over 0, then I would say, yes, Jocelyn, you should assume it probably doesn't exist and start testing paths. It's not always going to be the case. And if you see like something that looks like it might factor, you should definitely look for factoring as well. But a lot of the time it's not going to exist. Yeah.
So it's 0, 0.
0 over 0? Or do you mean the point 0, 0? Uh-huh. Yes, you should plug in 0, 0 because you could have a limit that's approaching 0, 0 where you're not going to get 0 over 0. For example, I could say, what's the limit as xy approaches 0, 0 of x squared plus y squared minus 9 over x plus y plus 3. And then I'm just going to be like, well, that's going to be 0 minus 0 plus 0 minus 9 over 0 plus 0 plus 3, which is negative 9/3, which is negative 3. So we always want to plug in the point just to make sure we're not getting 0 over 0, because if we're not, we're done.
So would you still plug in 1?
So what I would say is usually if the point isn't 0, 0, most of the time the limit's going to end up existing. Not always, but a lot of the time, just because it's not as easy to find paths that go through other points. Let's continue with this example for just a second. What if I said instead I wanted the limit as xy approaches negative 3, 0 of x squared plus y squared minus 9 over x plus y plus 3. Now I'm gonna get 0/0. And I will be perfectly frank, I have no idea if this limit exists or not, because I just made it up. But my default assumption would be it does not. So I'm going to try paths. And the easiest paths to try, if you're going through a point that is not the origin, I mean, true, actually, this is true whether or not you're going through the origin or not. The easiest paths to try are just x equal to the x coordinate and y equal to the y coordinate. Those are the first two paths you should almost always try. A lot of times I've been skipping one of them because I know it's going to give me the same result, but you should still try them. So let's try this. It might not work out. That's part of math. Sometimes things don't work out. I'm writing the wrong things here. So my path is going to be x equal to -3. So I'm going to do the limit as y approaches 0 of -3 squared plus y squared minus 9 over -3 plus y plus 3. The 9 minus 9 is 0. The -3 plus 3 is 0. So I'm left with the limit as y goes to 0 of y squared over y, which is the limit as y goes to 0 of y, which is just 0. All right, so let's cross our fingers and hope that when we do the other path, we don't get the same result. I have no idea if it's going to work or not. So if we try y equals 0, now we're going to do the limit as x approaches -3 of x squared minus 9, because the y is 0, over x plus 3. And thank goodness it's going to work out, I think. Yeah, cool. So this one, we can find that limit by factoring and dividing through. So I get the limit as x approaches -3 of x plus 3 times x minus 3 over x plus 3. X plus 3 divided by x plus 3 is 1. I'm left with the limit as x approaches -3 of x minus 3, which is -3 minus 3, which is -6. Those values are different, so the limit does not exist. So this limit, right over here, the limit as x, y approaches -3, 0 of x squared plus y squared minus 9 over x plus y plus 3 does not exist. And that's typically how I would try something that I'd never seen before. I would try picking paths if I had 0/0, and then if I didn't see an obvious factoring, right? This to me, there's no obvious way of factoring that. So I started just using the usual thing. Let's see what's happening in the chat over here. Oh, okay, cool. Right on. All right. Yeah, I feel like we probably said enough about, oh yeah, question. Well, it was a different limit. So I did two different limits here. The first limit was as xy approaches 0/0. And that was easy. We plugged it in, we got -3. The second limit was as xy approaches a different point, -3, 0. So it's a totally different problem. Happened to be the same function, but a different limit altogether. Yeah, and I think that's, I feel like all these just don't exist. Yeah. So let's go ahead and I think we should spend a little bit of time talking about partial derivatives. Yeah. Okay, let me gather my notes. So many notes. There we go. So what I should say first about partial derivatives is this idea of a path is still very prevalent. Just like when you find a limit and you're trying to find, like, you're letting x equal 0 and you're seeing what's happening to the function as you stay on the path x equal to 0 or y equal to 0 or x equal to -3 or whatever we pick. The same kind of ish thing is somewhat true when we talk about partial derivatives, because what we're really going to be doing is say, oh, we're going to hold y to be constant and ask how the function is changing in the x direction. Let's look at an example. Yeah. So let's say we have this function. And let's label things here. Partial derivatives. And what I should actually say here is the idea maybe is takes a little bit of work to grasp your mind around, but the actual execution is really straightforward. The execution for partial derivatives is just you pretend like the variable you're not differentiating with respect to is a constant. That's all you really have to do to make it work. We'll do some practice, but I should show you the idea first. So let's say we have this function. F of xy is equal to 9 minus x squared minus y squared. This graph, the graph of this, the surface is an upside down paraboloid. If I draw it, it looks like this. And there's my y-axis, my z-axis, and there's my x-axis. What we're going to do is we're going to say, okay, well, I want to know what's the derivative of this surface, or what's the slope of the tangent line to this surface in the direction of x when I hold y equal to 2. So I'm going to, now normally I will just point out, you don't actually have to set y equal to any particular value. We're going to do that so we can see what's happening. So if I set y equal to 2, that's cool. I'm like, I don't know. I'm like, people are looking at me like, I think I have 23 minutes still. Okay, so over here at 1, 2, 3. So here's y equal to 2. And let's hopefully I can get this looking pretty good. So there's the trace is when y equals 2. It's kind of like a level curve, except you're not going up, you're going to the side. So I'm setting y equal to, just like you could set z equal to something and get a level curve. Yeah. So what I would say here is, so right here, this parabola I've drawn, if I set y equal to 2, I'm going to get f of x comma 2 equal to 9 minus x squared minus 2 squared. Or more easily, I'm getting z, right, because that's another name for f of x comma y, equal to 9 minus 4 is 5 minus x squared. So this parabola that I've drawn here is really just the parabola in the xz plane where y is equal to 2. That looks like this. Shouldn't what be z? Yes. I was like, I'm not, yeah, thank you. I'm like, what are you saying? Yes, that should be z. Good call. Sorry, I was not understanding. You're 100% right. Sometimes I miss things. Okay. This pen really smears. Okay. So now we're going to ask, what is, I know I'm write this the right way. Yeah. So I want to know, what is the slope of the tangent line in the x direction? So in other words, that is, what's the partial derivative? Partial derivative with respect to x. There's a couple of ways of writing this. Some different notations are, you can either write del f del x, not a d, it's a del, it's a little curlier. No one's going to notice if you accidentally write a d instead of a del. But I'll just tell you, a del means partial, whereas a d means your function is only a function of one variable, so it's the whole derivative, not a partial derivative. Another notation for this is f sub x, the partial derivative of f with respect to x. Either way, you're looking at your function, 9 minus x squared minus y squared, and you're treating y as a constant like we have here and taking the derivative. The derivative of 9 is 0, the derivative of a constant is 0, the derivative of negative x squared is negative 2x. Same deal there. The derivative of this is negative 2x. So then I could ask the question, what's the slope at the point 2, 1? If I want to know what the derivative is at 2, 1, sorry, 1, 2, apologies. That's just going to equal negative 2x evaluated at x equal to 1 and y equal to 2, which is negative 2. Let me graph it for you. So what we're saying here is at this point right here, when x is 1 and y is 2, I will point out y isn't on this graph here. The slope of the tangent line is negative 2. I'm going to draw it again in 3 dimensions. Over here at x equal to 1 and y equal to 2, which is about right there. There's x equal to 1 and y equal to 2. I'm going to go up to my curve and find the slope of the tangent line in the x direction. And that slope is negative 2. Because I move, and so when I say the x direction or the y direction or the z direction, what I mean is the positive x or y or z direction. So if I say in the x direction, I mean as I move out towards you, right? Because the x direction points out towards you, the slope is negative 2. Because I'm going down as I move in that direction. Okay. What would the partial derivative of the function be with respect to y at that point? Well, let's try and fit it on the same page so that we don't have to move away from my lovely picture here. What's del f del y or fy? Well, if I take the partial derivative with respect to y, pretending x is a constant, derivative of 9 is 0, derivative of x squared is 0, derivative of negative y squared is negative 2y. And if I plug in the point, del f del y evaluated at the same point, 1, 2, I'm going to get negative 2 times 2, which is negative 4. So this is my original function, right? I'm taking the derivative with respect to the variable y. So the derivative of 9, derivative constant 0. I'm pretending like I'm holding x, I'm not pretending, I am holding x constant. So I'm only moving in the y direction. I can't move forward or backwards. I can only move left or right. And when I hold x constant, well, x is constant. If I'm holding x constant, is x changing? No. And the derivative of something that doesn't change is 0. So the derivative of negative x squared here is 0 if we're differentiating with respect to y. And then the derivative of negative y squared, well, y is changing. Its derivative is going to be negative 2y. And so my picture is not, yeah, I can make this happen. Okay. So I'm going to try and draw the parabola in the other direction as well. So if I look at here, so I look at the plane where x equals 1. Whew. Okay, pray for a second here. Here's my parabola. Supposed to go through that point over there. Sure, we can pretend like that works. Okay, it's not perfect, but it's all right. So there's the parabola. Instead of the red one where y equals 2, the black one here is where x equals 1, right? I just pushed forward 1 unit. And on that parabola, x doesn't change. I'm not moving backwards or forwards on that parabola. It's all in the plane x equals 1. So the slope of the tangent line there, that slope is negative 4. I know I've not done the best job drawing it because it should look a little bit steeper, but it doesn't. But that's the idea, is that in the Y direction, you've got one steepness, in the X direction, you've got another steepness. So that's the kind of physical interpretation of what partial derivatives really mean. You're holding one thing constant and asking, how is the function changing in the direction of the other variable? So we're really asking here, if I hold y constant, how is the function changes as x increases? Oh, well, if x is increasing, the function is going to be decreasing by 2 for every one that x increases. Over here, same deal, except now if we're holding x constant and y is increasing, the function is also going to increase by -2, decrease by 2 for every one that y increases. It just depends on how much you're getting depending on where you're actually out on the surface, right? The further out you go, the steeper things get because it's going like that. Yeah.
Why you said, why?
Because I was looking specifically at the point where x is 1 and y is 2, because I picked a point.
Oh.
Just to kind of show what's happening. So just like I was saying there, I could have picked anything. I happened to pick a point. I really picked a point that was in the first quadrant where x and y were positive because it's easier to graph. But really, you could have picked anything to see what the slope looked like in a different place. So for example, if I pick something over here instead, like if I pick the point, say x is 1 and y is -2, and this had been my point right here instead, then my partial derivative with respect to y would have been positive because I would have ended up plugging in a negative y value. At this point, x is 1, y is -2. And you can see that, oh yeah, the tangent line there, as you move in the y direction, which is from left to right, that the slope would be positive because the function's increasing as you move from left to right. So here I will just point out that fy at the point 1 comma -2 would have been -2 times -2, which is +4. So that slope there is +4, that slope there is -4. Okay. Cool. Let's get down to the nuts and bolts though. Let's do some practice. So when finding partial derivatives, the whole idea is that the one you're not differentiating with respect to, or the ones, because you could have a function of more than just x and y. You could have x, y, z, w, whatever. Whatever you're differentiating with respect to is your variable, and every other thing gets treated like a constant. So let's look at something not too terrible, like f of x, y equal to x to the 6th plus y to the 3rd plus x to the 4th times y to the 5th. And we're going to find the partial derivatives. And I would encourage you to get comfortable using Iota notation. So the partial with respect to x, del f del x, or fx. I'm treating y like a constant. The derivative of x to the 6th is 6x to the 5th. The derivative of y to the 3rd is what? 0. And now you have x to the 4th times y to the 5th, which is a function times a constant. Constant multiples hang out, as I like to say, right? Just as a reminder, if you take the derivative of, say, like 7x to the 6th, you get 7 times 6x to the 5th. That 7 hangs out, and you get 42x to the 5th. So when you have a constant multiple, it just hangs around. So y to the 5th is our constant multiple. It's going to hang around, and you're going to get x to the 4th times 5y to the 4th, which I personally would rewrite just slightly as 6x to the 5th plus 5x to the 4th y to the 4th. I would write this up. The numerical constants are in front, and it's alphabetical. X before y. Let's find the other one. Well, there's more than the other one. Let's find del f del y, also known as fy. So now the derivative of x to the 6th is going to be 0. The derivative of y cubed is going to be 3y squared. And the derivative of x to the 4th times y to the 5th is going to be 4x cubed. Oops, nope, not at all, James. Whoa. You guys let me get away with something. Sorry, let's back that up a minute here. Let's try again. I apologize. I was thinking of something else. I wasn't really thinking, I was just, that's an excuse. I just made a mistake. That's the real thing that happened. I made an error. That happens. Let's try this one more time. Our fx, which is del f del x, should have been 6x to the fifth plus 0 plus the derivative of x to the fourth is 4x cubed times the constant hanging out, which is y to the fifth. Apologies. If you think I'm making a mistake, you might probably be right. So don't, I mean, I know the other, when you were trying to say I was graphing something wrong, I wasn't getting it. You should still say something, even if you think I'm not going to get it. Keep saying it until I get it, or I will figure out what I'm doing wrong. So yeah, sorry about that. Everyone makes mistakes. I try not to, though, most of the time. So now let's find our fy, which is del f del y. The derivative of x to the 6 is 0. The derivative of y cubed is 3y squared. And now the x to the fourth gets to be the guy that hangs out. And the derivative of y to the fifth is 5y to the fourth. So here we're getting 3y squared plus 5x to the fourth y to the fourth. And that looks much more correct. Okay. Oh, yeah. So I know, yes, you want to say the derivative of the y thing is 0, but here's the deal. So let me, and I'm going to say this again. What's the derivative of 7x cubed? So let me, before we say anything, 7's a constant, right? Is its derivative 0? Well, yes, on its own, but not in this context. So let me actually say a bigger thing here. One way to think of this is to think of this as 7 times the derivative of x cubed. Constant multiples get to come out in front of a derivative, and you get 7 times 3x squared, which is 21x squared. Or if you like, we can use the product rule. So if you take the derivative of 7x cubed, it's equal to the derivative of the first thing, which is going to be 0, times the second thing, plus the first thing, times the derivative of the second thing, which results in the same answer. I get 0 times x cubed plus 7 times 3x squared. 0 times x cubed is 0, so I end up with 21x squared. So that's why constant multiples get to quote unquote hang out, is because either you're using the constant multiple rule, but really this constant multiple rule just stems from how the product rule works. The fact that if you do the product rule, when you take the derivative of the constant part, you do get 0, but then when you do the other half of the product rule, you're leaving the constant alone and multiplying by the derivative of the function part. Right, exactly. So, but if you want it here, right, like right here, where when the x, we're talking about this one where the x to the fourth hung out. So you could have said for this one, right, like if I'm taking the derivative of x to the fourth times y to the fifth with respect to y, I could have said, okay, it's going to be the derivative, so product rule, derivative of x to the fourth times y to the fifth plus x to the fourth times the derivative of y to the fifth. But the derivative with respect to y of x to the fourth is 0, because x to the fourth is a constant. But then the derivative of y to the fifth here is 5y to the fourth. So we're exactly getting this part right here like we would. You can totally do it using the product rule. It's just faster to say, oh, we're using the constant multiple rule, where any constant and x is acting like a constant, it gets to hang out. And you just multiply by whatever the derivative of the other part is. Okay. Let's find the second partial derivatives. So just like they have second derivatives in 17a, we have them in 17c. So I can find fxx, which is del squared f del x squared. It's just the derivative of the derivative. So the derivative of the derivative. So I'm taking the derivative with respect to x of the derivative with respect to x. All right, well, that's going to be the derivative of 6x to the fifth is 30x to the fourth. The derivative of 4x cubed times a constant is 12x squared times that constant. Let's find FYY. So FYY, or del squared F del y squared, is just the derivative with respect to y of the derivative with respect to y, which is just the derivative with respect to y of my Fy, which is 3y squared. You don't actually have to write all this out. Like if I was actually doing this and trying to do it efficiently, I would just look at this function and write down its derivative with respect to y. So I would be like, okay, I'm going to get derivative of 3y squared, which is 6y, plus my 5x to the fourth hangs out as a constant multiple, and the derivative of y to the fourth is 4y cubed. That's what I would actually do if I was taking the second derivative. I wouldn't write all this mess here, but I'm writing it so we can see the notation. And then we would simplify, because of course we would simplify. You get 6y plus 20, x to the fourth y cubed. Okay. There's one other thing we need to, well, actually, there's two other things we need to find, but really only one other thing. We need to find the mixed partial derivatives. We want to find fxy, which means you do the derivative of x first, and then the derivative of that with respect to y. Derivative with respect to y second. And here's some bad news. The notation here is, I'm not gonna say it's not that it's ambiguous, it's that it's reversed if you write it using the other notation. So this other notation, the del notation, called the Leibniz notation, the way you'd write this is del squared f del y del x. Sorry, I didn't make it up. The reason this is written this way is because this really means the derivative with respect to y of the derivative of the function with respect to x. So you're doing the derivative with respect to x first, and then the derivative of that with respect to y second. So that's why you write it this way, but that's why you write it that way. So yeah, they are kind of backwards from each other, and you just kind of have to live with that. There is some good news though, which you'll see in just a second. So don't worry too much about it. I have good news. So this is going to be the derivative with respect to y of my derivative with respect to x, which was 6x to the fifth plus 4x cubed y to the fifth. If we do that, the derivative of 6x to the fifth is going to be 0. There aren't any y's there. The derivative of 4x cubed y to the fifth is going to be 4x cubed times 5y to the fourth, which is 20x cubed y to the fourth. And now we'll find the other mixed partial derivative. We'll find fyx, which is del squared f del x del y, which is del x of del f del y. So you're taking the derivative with respect to x of the first partial with respect to y. So the derivative with respect to x of my fy, which was 3y squared plus 5x to the fourth y to the fourth. Okay, the derivative with respect to x of 3y squared is going to give us a big old 0. And then the derivative of 5x to the fourth times the constant y to the fourth is going to be 20x cubed times y to the fourth, which just gives me a 20x cubed times y to the fourth. Hey, look at that. They're the same. So there's a theorem about this, which is complicated, that says these mixed partials are the same under certain conditions. So what I should really say is these aren't always the same, but in this class they always will be. The function has to be moderately complex to have the situation where your mixed partials in the opposite order are not equal to each other. Like the easiest function that has this kind of thing happen where they don't equal each other is some strange piecewise thing where you've got all sorts of stuff. So any function that looks quote unquote normal, where you've just got like f of x, y equals stuff with x's and y's, and it's not like a piecewise function, you can have a relatively good expectation that the mixed partial in one order will equal the mixed partial in the other.